That's right, kids. Time to wake up and talk about the fundamental theorem of algebra. Yes, but first, a word from the dictionary. What does it mean to be fundamental? Okay, so the word fundamental itself, for our purposes, will be the noun, right? The central or primary rule or principle on which something is based. So, wow, this is big. This is really big, right? The fundamental theorem of algebra, the primary rule or principle in which algebra is based on. And really, not only algebra, but moving forward, the bigger stuff resides on the fact that this works. So let's take a peek at it. The fundamental theorem of algebra states that if a function, right, of polynomial degree n, right, so if f of x is a polynomial degree n, where n is greater than 0, then the equation f of x equals 0 has at least one solution in the set of all complex numbers. Okay, now we'll pull that apart in a minute. I wanted to move on to the corollary, right? So first off, corollary is a proposition that follows from, right, and often appended to, attached to, one that's already proven. So we're attaching to this fundamental theorem that says if a function of polynomial degree n, where n is greater than 0, right? So if you have a function where n is greater than 0, then the equation f of x has exactly n solutions, provided each solution repeated twice counts as 2 solutions, or each solution that's repeated 3 times counts as 3 solutions. So this is critical. Stick with me. What do we mean? The fundamental theorem of algebra implies that an nth degree polynomial function f has exactly n zeros. So how many solutions does this equation have? If you were to solve this for 0, how many does it have? 3, because n is equal to 3. Now, some of those may be repeating, some of them may not be rational, some of them may not be real. But they all fall under the complex set of solutions. So 3 solutions. How many zeros does this function have? 4. Same reason. So look, we've been teeter-tottering around this thing, dancing around this fundamental theorem. We're just basically stating what we know already, very formally. All right, so what do we know here? We know that we have this 5th degree polynomial, right? This is an expanded form, right? Just got to keep all this vocabulary going, right? I know that this is my constant, also my y-intercept. Got my lead coefficient up here as a positive 1. Since the degree of the function is 5, there are 5 zeros. Hey, no kidding. And then all the possible factors of 14 divided by 1, right, is just going to be plus and minus 1 times 14, plus and minus 2 times 7, right? So 7 and 14. These are all possible values we could use. So now I'm going to throw you some test zeros. How about we try f of negative 1, and we're going to try that one twice, and we're going to try f of 2. So let's just fill in the blank spaces here. As I said, we're going to use negative 1 twice and then 2. We already have the synthetic division laid out, so here was our original function. And this is where we stole the idea. The 1, right, is right here. Negative 4, positive 10, negative 13, negative 14, and that's 5, 4, 3, 2, 1, and a constant. So all our players are there. So 1 times our 1 gives us negative 1, gives us the negative 5. 1 times negative 5 gives us a positive 5, or negative 1 times that gives us a positive 5, gives us a 9. Negative 1 times 9 gives us negative 9, gives us a 1. 1 times negative 1 times 1 gives us a negative 1, gives us a negative 14, gives us a positive 14, gives us our 0, check. Okay, so now what? We try negative 1 again. 1 times the 1 gives us a negative 1, gives us a negative 6. Negative 1 times negative 6, positive 6, 15. Negative 15 gives us a negative 14, positive 14 gives us a 0 again. Boom. Let's try 2. 2 times 1 gives us 2. Negative 6 plus 2 is negative 4. 2 times negative 4 is negative 8. 15 minus 8 is 7, and 2 times 7 is positive 14, gives us a 0, check. And now we know that this is x squared minus 4x plus 7, because we've come down from the x of the 5th, the 4th, the 3rd, So this is our quadratic. So now we have factors of x plus 1, x plus 1, x minus 2, right? And these are our zeros. These are our factors. This is still a quadratic factor. It's a factor nonetheless. These are linear factors, right? And this is really super cool vocabulary to use on Scrabble. All right, so we have our linear factors here. These are all linear because they're x to the first power. And our quadratic factor is there. So now we're going to move on to breaking apart x squared minus 4x plus 7, which we can already see factors of 7 that add up to negative 4. I don't think that's going to work out very nice. I think we're going to need the quadratic formula. So let's review what's going on here. Since the degree of the function is 5, there should be 5 zeros. How many do we have so far? Well, we had a multiplicity of 1. That was the value of 2. So we're sort of working backwards. And then we had the negative 1 has a multiplicity of 2. Therefore, there are 2 complex solutions. And what makes them complex? Because it's going to be, something a plus or minus, a square root of something. It's not going to be pretty. So just a reminder, our quadratic formula is over here. The opposite of b, plus or minus the square root of b squared minus 4ac all over 2a. That's going to give us our zeros for x. Right? And here's my a, b, and c. So press pause and work this out on your own and see if you can get the same answer as me. Again, press pause, do this on your own. This is an active participation piece. Okay, so I arrived at 2 plus or minus I rad 3. Now remember, there's two things happening here. That's the 2 plus I rad 3 and the 2 minus I rad 3. So you combine that with my use of negative 1 twice, 2 once, and then these two. So I think that gives us the multiplicity of 2, 1, that's 3, 4, and 5 here. If you need to, press pause and check out the setup, the work as I work my way through this, and the simplification. If you can't do this, then get yourself a meeting one-on-one. This is on you. So let's see how this all wrapped up. We're going to write the polynomial function in completely factored form. So here's the factored form. So where does the x plus 1 come from? Well, remember that we had a 0 at negative 1 with a multiplicity of 2. And then we had a 0 of 2 with a multiplicity of 1. So the negative 1, 0 turns into our factor of x plus 1, and a multiplicity of 2 is where we get the squared from. Then we have 2, so x minus 2 is the factor. And then we had our zeros at our complex zeros at 2 plus or minus I rad 3. And there's two different values there. There's the 2 plus I rad 3 right here. And then there's the 2 minus I rad 3 right there. And remember, just like we take the negative 1 and we say x minus a negative 1 gets us the factor of x plus 1, same thing here. I'm going to say x minus the 2 plus I rad 3 and the x minus 2 minus I rad 3. And those are the other two factors. So now we just want to complete the drawing. I know this was an odd polynomial. So the lead coefficient was positive 1. So I know it's positive. So I know on the left side we're going down. On the right side we're going up. And I know at negative 1 it's going to be a touch and turn. I know that negative 14 was the constant on that, right? So I know that this is my y-intercept. So my y-intercept is at 0, negative 14. That's right there. And it's going to be a touch and turn at negative 1. So we're just going to bounce off of negative 1, come down here, and bada boom. Right? Not the most beautiful piece, but nonetheless. Note, only real zeros appear as x-intercepts, right? These are not real zeros, so they will not appear as x-intercepts. And then you have this word tangent. Tangent means just to touch at one moment. So we have this tangent moment, that touch and turn. And that's because -1 had a multiplicity of 2. But the graph crosses at 2 because it has a multiplicity of 1. Again, reviewing a lot of stuff that we've been doing. So what are you going to do? Here, you're going to find all the zeros of the polynomial function. How many should there be? There should be 3 zeros. Will they all be real numbers, rational numbers, complex values? Can't tell you that part. All I can tell you is I'm going to start by setting up my synthetic division. 1x to the third, 7x squared, 15x, 9. I should land with a 0. Who are all my possible zeros? Plus and minus 1, plus and minus 3, plus and minus 9. My hint, try -3. Try it more than once. And then provide your 3 zeros as your final set of notes. We'll be looking for it. On this problem, same scenario. You're going to finish this one on your own to have your notes as complete. So I see I have x to the 5th, so there should be 5 zeros. Okay. Now, who could they be? Plus and minus 1, plus and minus 2, plus and minus 3, plus and minus 6. One thing to watch out for in the synthetic division, I got my 1x to the 5th minus 2x to the 4th, no x to the 3rd, that's a 0. 8x to the 2nd minus 13x to the 1st, 6 should come out to a 0. All I'll tell you is that -2 may be a good one to check out, and maybe 1 more than once, just saying. But you're going to have to provide all your work to receive credit. The last part here is just sort of wrapping up something that I've already kind of touched on. If a polynomial function has real coefficients and a plus bi is an imaginary 0, then of course a minus bi is also an imaginary 0 because a plus or minus bi is the only way that could have shown up. So if this is 1, this is the other automatically. That's the complex, right? If you have that radical with a negative underneath it. The irrational conjugates theorem is essentially the same thing. That if you have a plus the square root of b, then obviously you have a minus the square root of b, right? So suppose yada, 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 right? So write a polynomial function f of least degree that has the leading coefficient of 1 and 3 and 2 plus radical 5 as zeros. Well, that means that you have f of x, right? Lead coefficient of 1, so that just means positive x to something. I'm going to leave that like that, just that thought, right? So if 3 is one of the zeros, then that's x minus 3. And then x minus 2 plus rad 5. And x minus 2 minus rad 5. Because remember, if 2 plus rad 5 exists, then 2 minus rad 5 also exists. And so I guess this is a third degree polynomial. All right, and some rapid fire practice, writing the polynomial functions. They're all going to have lead coefficients of 1, which means no fanciness out in the front, no negatives. So f of x, our -1, is a factor of x plus 1. Our 2 is a factor of x minus 2. And our 4 is a factor of x minus 4. So there we go. How about b? F of x, change colors. F of x equals x minus 4. And then we got 1 plus rad 5, so that's x minus 1 plus rad 5. And I'm just going to kind of squeak it off in the bottom here, and x minus 1 minus rad 5. Close, close. And there's our 3 factors. Down at the bottom, we have f of x is equal to x minus 2. Okay, so that's that one. And then just plus or minus 2i, so that's going to be x minus 2i, x plus 2i. And then we have the 4 minus rad 6. So I'm going to just sort of wrap this around here. It's also x minus 4 minus rad 6 and x minus 4 plus rad 6. So that's our 1, 2, 3, 4, 5 factors. And how did we know we had 5? We had the 1 right here, and then this is a complex, so that's going to be 2 zeros, and this is the irrational, and that gave us the 5. All right, last one. Back to red. F of x equals x minus 3. And then we have the 5 minus I, so we have the x minus 5 minus I. And of course, if 5 minus I exists, then that means that 5 plus I exists. They cannot exist without each other. And that's going to be an x minus 2. And there's our 3 factors. All right, you're on your own. Finish up those 2 examples and then submit these notes as completed. Give yourselves a round of applause. And before I leave, I just want to ask, are there any questions? That's what I thought.